Okay, let's do another example. So in the last one, we wanted to know how much product was formed, but sometimes you also want to know how much of a particular reactant you need. For example, in this question, asks how much oxygen is needed in order to completely burn 425 moles, which is about one tank of gasoline. And the compound indicated here is octane, which is the primary component of gasoline, although gasoline isn't pure, so there are some other things in there as well. But octane is the primary component. So anyway, we want to figure out how much oxygen we're going to need to do this combustion reaction. And so to do this, again, we're going to write the number 425, that's a known, under the coefficient for that molecule. And then we're going to write X under the unknown, which is oxygen. And then we set this up as a equation, an algebraic equation. And basically, when we rearrange it, so basically you can cross and multiply. So 2 times X is equal to 425 times 25. And then we need to solve that whole thing. It turns out that you need 5,312 moles of oxygen to do this reaction. So if you look at this, there's 2 moles of or 25 moles of oxygen per 2 moles of methane. So it looks like you would need quite a bit more oxygen than methane, and this is indeed the case. Here are some practice problems, and if I click right here, you can see the answers. I am not going to do these here. I will do some practice problems later on in a Zoom session, but I recommend that you try to do these and ask if you have any questions. So far, we've done problems. We've just figured out how many moles are formed from a certain amount of in a chemical reaction. However, what we often really want is to figure out the mass in grams that we want, because it's much easier to measure grams of something or mass of something than it is to measure moles of something. If you're in the lab, you can use a balance to figure this out. But you need to start out with moles because the coefficient is a ratio in moles. It's not the ratio in mass. So that's why we go through this whole process of converting. And if you do want to convert, then you can use the same little diagram that I show here. You can convert from moles, between moles and grams, and you can also convert between moles and particles. And you can start with particles and end up with grams going through the mole and vice versa. Okay, let's do an example where here we have lead chloride reacting with aluminum sulfate to form lead sulfate and aluminum chloride. So this is a displacement reaction. And the question asks, what mass of aluminum chloride is produced if 55 grams of lead chloride is used? So the first thing we're going to do is calculate the formula mass and convert it from mass to moles. So remember, we can't figure out the ratio like when we did that before, where we divide by to form the ratio. It has to be in moles because the mass of each of these substances is different. So we can't tell by just looking at the mass how much will be formed. So when we take lead chloride, lead has an atomic mass of 207 grams per mole. And so Cl2, it's like 35 grams per chlorine, and there's 2 of them. So when we add that all together, the formula mass of this compound is 278 grams per mole. And then what we do next is we have 55 grams and divide that by 277 grams per mole, and we end up with 0.2 moles. So that's how many moles of lead chloride we have. Now that we have that information where we're at in the problems that I just went over, and now we can go to the point where we put the number underneath the coefficient that it's related to. So 3 is the coefficient for lead chloride, so we're going to put the 0.2 underneath, and then going back and looking at our question, it asks how much aluminum chloride is produced, so that's where we want to put our x, and then we draw this ratio and cross multiply, and we get an answer of x equals 0.13 moles. So that is the number of moles of aluminum chloride that is formed. And now we have to, but it doesn't ask for moles, so we again have to convert back to the mass to figure this out. We're going to, at this time, need the formula mass of the aluminum chloride. So it's again this time it's 3 chlorine atoms, so 35 times 3, and then aluminum has a mass of 27 grams, and that, if you calculate that out, that's 132 grams per mole, and we have 0.13 moles of it. So 0.13 moles times 132 grams per mole, we end up with 17 grams of aluminum chloride. Okay, we'll solve another problem. In this one, it asks, if a lighter contains 50 grams of fuel, butane fuel, how many grams of carbon dioxide will be produced over the lifetime of the lighter? So again, for this kind of problem, since the stoichiometry indicates the ratio in moles, we need to convert to moles to answer this problem. So we have a butane, we have to first of all figure out the butane formula mass, and carbon is C4H10. Carbon has a mass of 12, and there's 4 of them, and then we've got 10 hydrogens, each with mass of 1 gram per mole. When we calculate it out, we get a formula mass of 58 grams per mole. And then what we can do is basically take 50 grams, which is the amount of butane that we're trying to calculate this stoichiometry for, and divide it by 58 grams per mole, and we end up with 0.86 moles. So that's how many moles of butane there are in 15 grams. Now that we have that, the next thing we do is write down the 0.86 under the coefficient for butane. And then we also write an x. We want to know what the ratio of carbon, or how much carbon is produced. We're going to put an x under carbon. That's our unknown. Then we write the ratios down. 2 over 0.6 equals 8 over x. And then we cross multiply to solve this. So x equals 3.44 moles of carbon dioxide. So that's how many moles are formed. But we now want to convert back to grams because that's what the question asks for. So we're going to calculate the mass of carbon dioxide formed. So again, we need to figure out the formula mass. So that's 12 grams for carbon, and then each oxygen is 16, and there's 2 of them. Add that all together, and we get a formula mass of 44 grams per mole. So in this case, it's 3.44 moles is how much we end up with. If we multiply by 44 grams per mole, we end up with 151.4 grams. So that is how much carbon dioxide is produced when 50 grams of butane is combusted. And I just want to mention here once again, make sure that you show your units when I'm trying to figure out whether to, I need to multiply or divide to do my conversion. If I write my units, I can figure it out. So 3.44 moles times 44 grams per moles cancels, and we end up with grams. And then up earlier, we were doing the opposite calculation where we had 50 grams and we were dividing by 58 grams per mole, and the grams cancels and we end up with moles. Okay, let's do one more problem, but this time instead of figuring out mass, we're going to figure out the number of molecules that are released. So we're again going to use a Bic lighter. And let's assume that one flick of the Bic produces or uses 0.03 times 10 to the 23rd molecules of methane. how many molecules of oxygen are used to light a cigarette. So let's just assume that takes one flick. So in this case, we have 0.03 times 10 to the 23rd molecules. That's what we're given. And now we're going to use Avogadro's number, or 6.02 times 10 to the 23rd molecules per mole. In this case, we need to divide by Avogadro's number so that moles cancels out, or molecules cancels out, and we end up with moles. And when we do that, we end up with 0.005 moles. So now I'm going to rewrite our equation, and we're going to then put this number underneath butane, which is what it represents, and we'll put an X under oxygen because that's what we want to find out how many molecules there are of. So now that we have that ratio, we can draw this as an equation and cross multiply. And when we do this, we end up with X equals 0.0199 moles of oxygen used. So that's moles of oxygen, but the question again is asking for molecules. So we're going to this time multiply by Avogadro's number, the number 0.0199 moles, times Avogadro's number, and then we end up with 1.2 times 10 to the 22 oxygen molecules. So that's the number of oxygen molecules that are used. Okay, here are a few more practice problems. I am not going to do them now, but I do recommend that you do them yourself on your own time, and I have the answers right here so you can check your work. I will go over problems like this in class. I'm not sure if it'll be exactly these ones, but similar ones. And if you do have a question, don't hesitate to ask. And that's all for now.